Good morning, geometry class, period 5. Today we're going to go over our guided practice problems for lesson 10.1, use properties of tangents. We'll learn what a tangent is and then how we can solve problems using it. First, we're going to start with some circle vocabulary. I've copied some diagrams from page 641 of your textbook, and we're going to go ahead and develop some definitions for the pieces that you see on each of these circles. Some of this vocabulary you might already know, some of it might be new to you. So on the left-hand circle, we have a definition of what a circle is. It will be the set of all points equidistant from a point called the center. I do have that center point labeled on that left-hand diagram. Next, we're going to take a look at what a chord is. A chord will be a line segment whose endpoints are on a circle. Notice that chord is completely inside the circle. It will start on the circle and it will end on the circle. So it is simply a line segment drawn from one point on a circle to another point. A radius you're probably a little more familiar with. It will be a line segment whose endpoints are any point on a circle and the center. So from the center to any point on the circle will be considered a radius. Diameter will be twice a radius, and diameter will be a chord that contains the center of the circle. So, looking at our diameter that we have marked in here, we notice that that diameter extends from one side of the circle through the center point to a point on the opposite side of the circle. Now let's take a look at the right-hand diagram. The right-hand diagram will probably have some words that are new to you. First of all, we'll define a secant. A secant is a line that intersects a circle at 2 points. So draw a line through a circle so it touches that circle at 2 points, and you have a secant line. Tangent. Tangent comes from the Latin word meaning touch. So a tangent is a line that intersects or touches the circle in exactly 1 point. And where it touches that circle at that 1 point is called the point of tangency. Now we're going to move into some examples where we're practicing with those words. So using our circle vocabulary from above, we're going to notice that line segment AC is a radius. Line segment AB is a diameter. Ray DE is a tangent ray because it touches the circle at 1 point, at point B. Line AE is a secant. It cuts through the circle at 2 points. For guided practice 1, we're going to notice that line segment AG is a chord. Notice that's a line segment, not a line. If we are talking about line AG, of course, then it becomes a secant, not a chord. And then finally, for the last part of guided practice 1, line segment CB is also a radius. We're going to take a look at guided practice 2 that does refer back to that same diagram. Name a tangent. Lots of ways to do this right, but the way I chose was line DE because line DE touches the circle at 1 point, point B. Finally, on guided practice 2, we are to name a tangent segment, and there's lots of possibilities. I have written down 2, but you only need 1 of those answers or another answer that is also correct. So a tangent segment could be DB, from D to B, B touches the circle at point B, or BE, or you even could name line segment DE or ED. Those would all be tangent line segments for circle C. Now we'll move into some problems where we are going to use this information and some theorems to answer questions that arise in the context of circles. Theorem 10.1, which I would like you to write down in your paperwork for your guided practice problems. Theorem 10.1 says that line M is tangent to circle Q if and only if line M is perpendicular to QP. It must be the case that line M is perpendicular to radius QP on that circle. Otherwise, if it were not, it would actually cut through that circle at 2 points and it would become a secant rather than a tangent. Theorem 10.2 relates the 2 segments that we can draw outside of the circle connecting at 1 point external to the circle. It says that if we have 2 line segments that are tangent to the circle, such that they form a common external point, those 2 line segments will be congruent. So in this case, if SR and ST are tangent segments, then line segment SR is congruent to line segment ST. Now we'll practice with some of these ideas. Guided practice 7 asks, is line segment DE tangent to circle C? Well, if line segment DE is tangent to circle DE, then a right angle will be formed in angle CDE, because remember, tangent lines are perpendicular to the radius whose endpoint touches the circle. So we're going to ask the question, is DE tangent to circle C based on the Pythagorean theorem? Now let's take a look at our diagram and notice how I've marked it up. We have a radius of 3 marked in twice. We have 2 as the length from point E to the circle itself, where it touches the circle, and then the radius from C to where it touches the circle. So notice that line segment CE is a total of 5 units. We need to put the radius of 3 together with the 2. Since 3 plus 2 is 5, line segment CE is actually 5 units long. And if, in fact, DE is tangent to circle C, CE will be the hypotenuse of that right triangle. So we're going to plug into the Pythagorean theorem to see if, in fact, it's true. And if it is, we will be able to conclude that line segment DE is tangent to circle C. So here I am now plugging into the Pythagorean theorem and asking, is CD squared plus DE squared, in fact, equal to CE squared? Here's my numbers for that. 3 squared plus 4 squared, is that equal to 3 plus 2 quantities squared? Remember, 3 plus 2 is the length of the entire possible hypotenuse, which is from C to E. So I'm going to work that out. 3 squared is 9, 4 squared is 16, 3 plus 2 is 5, and 5 squared is 25. And since 25 is equal to 25, I can now conclude, yes, line segment DE is tangent to circle C, because we have a right angle formed, proved by the Pythagorean theorem. Guided practice 8. Guided practice 8 asks the question, what is the length of the radius? Now we're told that line segment ST is tangent to circle Q, so we know a right triangle has been formed, and we can use the Pythagorean theorem to find out the unknown radius length. Remember again that from Q to a point on that circle, that's going to be R, and from that point on the circle to that external point T is 18. That means that line segment QT will be R plus 18 put together. So we'll use that for the hypotenuse's length. R plus 18 will be the hypotenuse length of this triangle. Plugging into the Pythagorean theorem, we will have R squared plus 24 squared for the 2 legs of that right triangle. That has to be equal to the hypotenuse squared, which will be R plus 18 quantities squared. Now we have to remember how to square a binomial, so I'm reminding you about FOIL, where we use first outside, inside, last to multiply R plus 18 times R plus 18. You're going to notice that there is a 36R that shows up when you multiply that binomial squared. That 36R comes from the inside and outside terms, 18R plus 18R. Okay, so moving down, we have R squared plus 576, that's what 24 squared is equal to R squared plus 36R plus 324. We then subtract R squared and 324 from both sides of our equation, and we arrive at the result 252 is equal to 36R. When we divide 252 by 36, we find that the radius is 7 units long, and we're done with that problem. Moving into our last guided practice problem. We have a circle with 2 radiuses drawn in at right angles to their tangent lines. The tangent lines that connect at an external point outside the circle are labeled as x squared and 9. Theorem 10.2 told us that those 2 line segments that meet at that external point outside the circle will be congruent, so we can with assurance state that x squared must be equal to 9. Then we take the square root of both sides of that equation, and we find that the values of x could be both positive and negative 3. That concludes our guided practice problems for lesson 10.1. Now it is time for you to continue on the homework assignment and have that ready for our next session. We'll see you then.